All right, so for today and tomorrow, we're going to be dealing with wind power, wind energy generation. So first off, on this topic, brief history of wind power and wind energy. So it's been around for centuries, even over 1,000 years. Way back in Persia, been wind-powered organs been made. So you see this guy up here, some wind blades, so kind of wind turbine. As the wind goes through there, spins this thing around. That generates the compression for the air going through the organs. Northern European windmills obviously been around for centuries, especially places like Holland. Hundreds of years had these windmills, so big blades covered in material generally to catch the wind, spins around a shaft. That shaft is then used for milling grains essentially. So that's how that was done in the last 100 years in Northern Europe. And then you realize that from this you make energy, so higher, more modern scale wind turbine, standard 3-blade design that we see a lot, not only around the oceans. So a lot of Northern European countries have these sitting out in the ocean. A bit north of here, up in Palm Springs, there's a lot of those hanging out on the side of the highway, you may have seen. So it's good to know where wind comes from. So generally wind is caused by a variation in pressure. So as there's different pressures, the fluid or air will move to different locations. It's at a place that has really high pressure, it's going to move to a place of really low pressure. So any sort of pressure difference will make the air move. This happens a lot from temperature. Temperature changes the pressure, and so that's going to again causes air motion. And so there's a lot of different scales of wind motion. The planetary scale, so going around the entire planet. Synoptic, kind of more in a state of California type of level. Mesoscale is kind of more of a city level, and then microscale going around buildings and things of that nature. A couple different wind types as well. There's polar easterlies, dry, cold, prevailing winds blowing from high pressure areas, polar highs around the North Pole and South Pole, and that blows to lower pressure areas that are in the westerlies. So these westerlies are kind of between 30 degrees and 60 degrees of latitude. So basically kind of where we are and further north. And these guys generally go to the west, so from east to west. So you see it in this figure here, blowing across the northern hemisphere east to west. Southern hemisphere, same thing, east to west. So those are the westerly winds or anti-trade winds. And the trade winds are the opposite direction, so generally going towards the west. And then northern hemisphere comes to the northeast, so not only straight to the east, but also a bit down to the south. Opposite in the southern hemisphere, coming up a bit, as well as going east. So those are the kind of large-scale wind currents affecting the Earth. There's also smaller scale ones. The jet stream around the North Pole that we sometimes affects our weather, especially in middle parts of the U.S. And all sorts of varied other kinds of winds, geostrophic, thermal, katabatic and anabatic winds. So these are topographic winds, so coming around mountains, going down, downslope winds, and of course sea breeze and land breezes, different temperatures from around the ocean than the land around it. Again, causes these pressure differences and winds to form. And so all sorts of other things can happen, hurricanes, things of that nature, dust devils in the desert. So many sources of winds, but obviously if you want to do wind power, you want kind of a stable source. So those planetary scale ones, kind of the most stable. So obviously if we're doing wind power, you need some sort of propeller to actually turn. And so what we have, instead of a propeller, thinking of like a plane as a propeller, that propeller is turned by an engine, which then pushes the wind, and that causes the plane to move. Kind of doing the opposite thing here. You want the air to come in, hit the propeller, turn the propeller, and then from that get some useful shaft energy out of it. But the analysis of the propeller is kind of the same, whether you're looking at it from the wind energy generation standpoint or from the airplane standpoint. So from the airplane standpoint, we have this propeller spinning around. Then we're going to have some propeller wake. So that's going to push the air. It's going to push the air closer to the shaft more than to push the air further away from it. So you have this wake that kind of bulges out in the middle. We do a control volume analysis on this guy. So propeller kind of right down the middle here has some diameter D. I have some velocity coming in, some velocity going out. Pressure distribution, so again, right where the propeller is, it's sucking the air, causing low pressure, pushing it out, causing higher pressure. The slipstream boundary is basically everywhere where my propeller sucks in the air. So anything outside this, that air is not being affected, just goes straight through, has that same velocity at the other side. So everything inside here is actually having its pressure and velocity changed by the propeller. So as I go through the propeller, I gain an additional velocity. So my velocity coming out of the slipstream, assuming to be constant velocity, v plus delta v. So that's using some idealizing wakes. That's ideal wake. Everything comes out at a constant velocity. There's two ways to analyze this flow. There's momentum theory, which is a control volume analysis, basically the picture we saw on the last slide, looking at momentum coming in, momentum going out. Rotor, the propeller model as an infinitely thin disk that induces a constant velocity along the axis of rotation. So again, assuming completely constant velocity everywhere throughout this. From that, I can figure out the slipstream speed, so what the change in velocity is, the thrust, how much force or energy is being put in, same thing with useful power. And again, that's all neglecting friction. The other way to analyze this is something called blade element theory. So you're actually looking at the propeller blades themselves and want to calculate that interaction between those blades and the stream of fluid. To do that, you basically break down the blade into a bunch of small parts and find the force being exerted on the fluid from each of the small parts and integrate that over the entire blade over one revolution. And that can give you the forces and moments produced by the entire propeller. A lot of times these two are actually combined to make something called blade element momentum theory. So it combines analysis of both of them to kind of give you everything you need to know. So for the control volume analysis, again, looking at that same control volume we saw a couple slides ago, thrust produced, Ft, is m dot times the change in velocity. So again, that's just doing control volume analysis, force in minus force out, just m dot delta v. Again, assuming incompressible flow, neglecting any friction or heat transfer. To find the power, we can look at the increase in kinetic energy. So I can increase in kinetic energy. At the end, I have some velocity v plus delta v. At the beginning, I have some velocity v. So my end kinetic energy v plus delta v squared over 2. Coming in is v squared over 2, all times m dot. So that's my change in kinetic energy. Gives me the power. Then I can expand this out and kind of combine those terms. I get 2v delta v plus delta v squared over 2. Then I can pull out a delta v and a v, and gives me m v delta v 1 plus delta v over 2v as my change in kinetic energy, or as a power. And so the useful power is the thrust, the force, times velocity. So standard equation for power, force times velocity, force of m dot delta v, velocity times v, I get mv delta v. And so my propulsion efficiency, useful power coming out minus power going in. So power going in is this change in kinetic energy. Power going out is this force times velocity. So mv delta v on top divided by mv delta v 1 plus delta v over 2v on the bottom. So those guys cancel out. All I'm left with is this guy, 1 plus delta v over 2v on the bottom. And then that I can just kind of multiply by 2v to get rid of this compound fraction on the bottom. So 2v over 2v plus delta v gives the propulsive efficiency of this propeller. So you can see that for any propeller, I can increase propulsive efficiency by either reducing delta v. So if delta v was 0, propulsive efficiency would be 1. So that's 100% efficient. Of course, it's not doing anything either. So that's not great either for that aspect of it. The other way I can do it is by increasing the velocity. So this velocity v is whatever speed the plane is flying, if you're in a plane, or the incoming velocity of air. for the wind turbine. So if that gets faster, you're going to get a better propulsive efficiency out of it doing that. For a constant thrust, the change in velocity can be reduced by increasing the mass flow rate, m-dot, as more fluid is accelerated over a small speed increase. More mass flow can be handled if propeller diameter is increased. So again, the bigger the propeller, the more mass flow rate you're going to have. But the overall size of the propeller and tip speed are limited by compressibility effects. So again, if they have a really big propeller spinning around, the bigger the propeller, larger diameter, is going to give you a larger linear speed at the tip of the propeller blade. And so keep on making it bigger and bigger. You keep getting bigger and bigger speeds out there. And eventually those bigger speeds are going to lead to either cavitation if you're dealing with liquids. So if you're in an underwater environment with your propeller, you'll end up with cavitation at the tips of the blades. Or if you're in air, you'll eventually end up with a Mach number getting closer to 1, and therefore you'll end up with compressibility effects. So those are two things that propellers aren't necessarily made to handle. So you kind of want to, you're limited in your size of propeller based on those. Same principles used to increase the propulsive efficiency in a turbofan engine. So a turbofan engine, unlike other turbojet engines, jet aircraft, is that there's a big fan that kind of goes around the engine. It's even bigger diameter than the engine, and that's kind of used as a propeller to suck in more air outside of the engine core. So outside of the part that's actually being added jet fuel to and being combusted. So the other way to analyze these things, blade element theory. This can be used to determine the effects of blade aerodynamic drag on the propeller efficiency. The blade spacing is large and the disk loading is light. The ratio of the thrust to swept area is small. So basically what you want to have are blades that look a lot like an airplane propeller, so they're very thin and spaced apart a lot. Another good example of that is the standard wind turbine that we see these days, the 3-blade design. You have very thin blades, and there's only 3 of them, so they're spaced really far apart. So because of that, the wake from one does not really affect the other, so therefore you can just kind of treat these as independent blades, so I don't have to worry about how the wake of one blade is going to affect the incoming flow of the next blade. So each blade can be treated completely independent. It makes our life a lot easier, blade element theory. So in those cases, I can get approximate relationships for torque and thrust developed by this propeller. Again, it's most accurate because I'm making this assumption of very thin blades that don't interact. So these results are going to be most accurate for those types of blades, or those types of propellers. So the way we do this, we're going to look at this depiction of my propeller blade. So here's my propeller blade. This is the plane of the propeller disc, so it's spinning around. Basically, this is my axis of rotation right here, and it's spinning around in and out of the page around that. And so I could have some sort of pitch angle outside of the plane of the propeller disc, have my kind of airfoil looking like propeller. And then I have some incoming velocity coming in, so this is my airspeed. And then this thing's rotating around it, as I said, in the plane of the page. And so there's some blade speed. We used to call that U. It's R times omega. So again, that's just R, how far I'm out from my center of rotation, times omega, the rotational speed of this propeller. This drawing isn't super good in the sense that it's kind of 3D. So this is not necessarily going straight left and right, because of if this guy was straight up and down, kind of going this way, then that would be that way. But that's just the rotational speed of the blade. So the linear speed of the blade. All this is done relative to a stationary blade. So I'm kind of assuming this blade is my reference point. So every velocity is measured with respect to this guy staying where he is. And so there's a fluid motion based on the fact that this guy's spinning around. So that's what R omega is. And then again, incoming fluid velocity gives me this resultant overall relative velocity vector V of my incoming air. And that has some angle of attack relative to the propeller itself. And from that, I can get lift and drag forces acting on this propeller, drag force in the same direction as my incoming flow. So this guy is kind of my reference line in terms of angles for lift and drag. So drag is the exact same angle as that guy, lift perpendicular to him. So what else have I not mentioned here? So again, this blade's at some angle, so some pitch angle with the propeller disc. This guy has some thickness dr, so in and out of the page, this guy comes in and out some distance dr. As I said, flow is relative to the propeller blade, so this guy's kind of stationary. This guy is my incoming flow, dr. Lift and drag forces measured respectively to that, incoming velocity. So again, drag in the same direction, lift perpendicular. The angle between VR and the plane of the propeller disc is called the effective pitch angle. So it's actually not shown on here, this phi. That's actually this angle right in here. So the plane of the propeller disc is the same direction as my r omega vector. So this angle right in here between r omega and VR is my angle phi. It's also the angle, if I drew a horizontal line here, that'd also be the angle between this horizontal line and my drag force. So my lift and drag force is again inclined at this angle, phi, to the rotation axis. My relative flow speed, VR, is going to depend on the peripheral blade speed, so r omega. So the faster this propeller spins around, the bigger this vector r omega is. Also depends on my incoming wind speed, v. So again, faster incoming wind speed gives me a larger value of this vector v. So this actual velocity VR I care about is going to depend on those two guys. Those two guys, again, the bigger this guy is or the bigger that guy is going to change this angle of attack. And so that guy, angle of attack, is also a function of both this incoming wind speed and the rotational speed of the blade. To look at a free body diagram of this airfoil element and look at the forces on it, so I have a lift force and a drag force. I want this parallel to the velocity vector v, so basically parallel to my incoming flow stream v. So now I'm looking at in this direction, basically standard xy coordinates, the y direction essentially, straight up and down the screen. I have some contribution from lift, which is whatever my lift force is, L times cosine phi, and that's going up, so positive. And then my drag force D, again, that's at some angle phi with respect to the horizontal line. I only want the y component of that, so that's a sine phi there. Technically, this guy's going down in the up and down y direction. So total force dl cosine phi minus dd sine phi. That's my elemental element of force from this little part of the blade in the up and down, what I'm going to call a y direction right now. Again, same direction as this velocity, incoming velocity vector v. Then lift and drag forces depend on lift and drag coefficients. So my lift and drag forces is 1/2 rho v squared times the chord length times the thickness. So 1/2 rho v squared times area. In this case, the area is, again, the chord length c, and this thickness dr. And then CL for my lift coefficient, cosine phi, CD for my drag coefficient, sine phi. So again, chord length, basically the length of this dashed line between the tail and the leading edge of my airfoil here. So C is that dashed line from there to there. So that's my overall thrust produced by this propeller. Now, in general, due to the fact that my blade is not nice, even thickness dr the entire way, the blade generally is going to twist a little bit, so it doesn't just go straight out. There's a little bit of a twist to it. If you ever look at a propeller blade, there's also taper in the blade, so they're not the same thickness the entire way through. Radial variation of blade peripheral speed. So again, that value of r omega is going to depend on r, depends on where I am on the blade. So CL, CD, VR, C, and phi will all be functions of r along the entire blade element. So what we're going to have to do is basically integrate those little functions we had before over the entire blade, basically from the bottom of the radius all the way out to the top end of the blade. Before we do that for the force, I want to also make the torque. So torque is essentially just R times the force. This is the force we had before. Multiply that by my distance R from the center of my propeller. And I get the incremental element of torque from that, again, small area of the blade. Everything here is the same other than I have this extra factor of R sitting in here for the torque. So 1/2 rho V squared, VR squared, RC dr, and CL sine phi, plus CD cosine phi. Plus sign because, again, right-hand rule, I'm dealing with the torque now. And so it's R cross F officially. And so both of these guys are actually working to spin the blade in the same direction he's going. If we look back at this picture, so I'm assuming this guy's spinning around. They're both pushing him. This guy's spinning this way, essentially, to the left. They're both pushing to the left. So they're both creating a positive torque to make this guy spin around. So that's why these are both positive. But in force, there was a minus sign, because that force was y direction, up and down. So again, I want to integrate these guys over the entire radius of my blade. So from R equals R hub. So generally it's not 0 because you have some sort of circular hub that the propeller is attached to. So it's not necessarily R equals 0, but some radius of the hub all the way out to some, whatever the end of the blade is, some radius capital R. The other thing we need to worry about is there's n equal independent blades. So I want to do this for the entire propeller. Each of these elemental ones was only from one of the blades. So again, if I have one of those like 3-bladed wind turbines, I need to multiply by 3 because I'm going to have 3 blades. So I just put this n in here to make that work. So 1/2 rho V squared. VR is going to depend on where I am, the distance R, but V is not. So my incoming blade speed, I'd rather have that in there. So I'm going to replace my VR with a V, but I can't just do that because they're related. V is VR sine phi. Again, I know that this angle in here is angle phi. So VR and V are related. So V is just this guy times sine phi. So using that, VR is V over sine phi. So I can replace this guy with V squared and then have a sine squared phi on the bottom. So sine squared phi is going to depend on R because phi depends on R. And then obviously R depends on R. CL and CE depend on R. So these are basically my equations. And I'm going to have to figure out how all this other stuff depends on R to actually do this integral. So these are just kind of left the way they are. Because at this point, I need to know how these guys all depend on R before I can actually evaluate this integral. So those are my general equations for the force from thrust, essentially, from my propeller, and the torque produced by the propeller as well. And I'm pretty sure that should be plus sign. Because of the plus sign here. This guy's minus though, because again, minus sign, y direction, plus sign, both spinning in the same direction. So a quick little example of this, I want to estimate the startup thrust and torque for a propeller consisting of n independent blades, constant chord length, constant angle with respect to the actuator disc plane. So very similar to what we did. This will be slightly simpler though. I'll be able to actually evaluate those integrals. So because I'm dealing with startup, my local wind velocity V is assumed to be 0 because there's no incoming velocity at startup. Also assuming a constant angular velocity, so my entire propeller spinning around the same speed. I don't want to go with the equation that just derived. I don't want to start down here essentially because my V is 0, incoming speed V is 0, so I don't want to necessarily start here because that's just going to give me 0 for both of those. What I want to do is take one step back essentially to back up to here. Actually not that far. I want to back up to here, I guess, for the forces back up to there. And so I have this factor of VR. VR I changed to V over sine phi in the previous equations. I don't want to do that because sine phi is going to be 0, because if I have 0 incoming velocity, this VR is just equivalent to R omega. So instead of making VR V over sine phi, now what I want to do is make VR the same thing as R omega. So replace this guy with R omega. replace this guy with R omega for the torque, and then integrate them like I do down here. So doing that, I get 1/2 rho omega squared n, and the stuff that depends on R, again, the angles. So I have CL cosine phi minus CD sine phi, R squared CDR. And then same thing for the torque. Torque just has an extra factor of R in it. So R cubed instead of R squared. And this again should probably be a plus sign. There we go. So now I just want to integrate those guys. So integrating these guys, again, at 0 startup speed, my angle phi is 0 because I have 0 incoming velocity. So I have 0 phi. So that's just going to give me a CL from this guy. That's going to be 0. Basically, what I'm integrating here is CL times R squared. Integral of that, I can pull the CL out. So 1/2 rho omega squared n chord length in CL, R squared from R hub to R. That's just R cubed over 3 from R to R hub. So putting these all together, and it's 1/6 rho omega squared NC CL R cubed minus R hub cubed. So this again, total radius to the tip of the blade minus where the blade starts at the hub. Again, same thing for torque, very similar integral, but now I have sine first and cosine. I should probably plus. So now it's this guy that stays around. So now it's the CD that stays around because, again, sine 0 is 0, cosine 0 is 1. So now I have CD instead of a CL, and I'm integrating R cubed instead of R squared. Other than that, exact same thing. So my torque, 1/2 rho omega squared. Number of blades times C. Drag coefficient, R to the 4th over 4, minus R hub to the 4th over 4. Put that all together, 1/8 rho omega squared n, C, drag coefficient, again, radius to the 4th, outer radius, minus inner radius, again to the 4th. So those are my expressions for the thrust and torque from this blade at startup. A couple notes on this. That seemed like relatively simple, not only for the expression, but for the integration itself. I'd made a lot of assumptions. I assumed that the lift and drag coefficients were constants with respect to R, which may or may not be the case because as I change my R, I'm going to be changing my speed, and generally CL and CD are functions of speed as well as the local angle of attack. So a lot of things that were kind of oversimplified in that example. At the startup speed, at V equals 0, angle of attack is equal to the blade inclination angle, so alpha equals theta. As I mentioned before, lift and drag coefficients generally given at high Reynolds numbers. So usually the lift and drag coefficients that I have, I can only find those at high Reynolds numbers. It's kind of hard to find those at 0 velocity because at 0 velocity there is no lift or force or drag, so why would you need them? So usually we find lift and drag coefficients only at higher Reynolds numbers because that's when you're flying. Doesn't make sense to have them if you're not going to be flying. Again, if I actually wanted to evaluate the previous expressions to find values of CL and CD, those would be hard to come by. Basically, the point of this is that CL and CD values are sometimes hard to come by. Sometimes they depend on a lot of things. So I want to make sure you're using appropriate values anytime you use any of this. So as I mentioned, these expressions fairly easy to derive, fairly difficult to evaluate because of all these concerns. So a lot of things depend on a lot of other things. The CL and CD values depend on a lot of things. Angles depend on a lot of other things. And so there's a lot of functions inside those integrals if you're going to do it using the more complicated expressions, the ones that we saw just before the example. Even if the geometry of the propeller is adjusted to give constant pitch, so again, generally these propeller blades taper and they twist and do all sorts of things. Even if they don't do that, still end up with a fairly complicated flow field. Angle of attack across the blade elements usually does vary, even if you have a nicely shaped propeller. So normally what we do for this is either numerical analysis to predict local flow velocities. So usually the equations we saw aren't very used very often. They're kind of there for illustrative purposes, kind of show very basics of what's happening. The other option is to use propeller performance characteristics that have generally been determined experimentally. So they do a bunch of experimental results, trying to figure out what the efficiencies are, what the torques generated are, what the thrust or forces generated are. So kind of see two pictures here that indicate these propeller performance curves. So for marine propeller applications, so basically through liquids, like propeller on the back of a boat kind of thing, you find the thrust coefficient CF and efficiency, as well as the torque coefficient CT. So you kind of see how those change with this thing called the speed of advance coefficient J. This is related to the incoming velocity that we'll see on the next screen. So you can see that for marine applications through liquids, as well as aerial applications through gases. So you can see these efficiency and force, and in this case, power curves. So again, these are generally, again, dimensionless parameters. Efficiency is usually dimensionless. C tau, CF, related to the force and torque, but they're dimensionless versions of them. And so dimensionless independent variable is a speed of advance coefficient called J, which again is related to my velocity V over n times d, n being the rotational speed in revolutions per second. So basically the same as omega, but different units. Omega is always in radians per second, and in revolutions per second, as opposed to radians per second. And then d by diameter. So that gives you a dimensionless value for the x-axis that these things are compared to. Then my dependent variables, thrust coefficient CF, torque coefficient CT, power coefficient CP, and propeller efficiency, eta. So my force is just, again, force on top, and then whatever units of force I get from the bottom. So rho n squared d to the fourth, give me units of force, so that gives me a dimensionless value. Torque, I need an additional radius or diameter, so rho n squared d to the fifth gives me units of torque. And then power, I need an additional per second or per time, as well as energy. So I need another distance and another time. So P power over rho n cubed d to the fifth, units of power there. So dimensionless version of power, CP. And of course, eta, power out over power in. Kind of saw this guy before. Force of torque times velocity divided by the power input, P in. So these performance curves, both marine and aerial applications, show similar trends. Thrust and torque coefficients are highest, and efficiency is 0 at 0 speed of advance, so at very low speeds is when I have the highest values for torque, force, and power. That's where they're all the highest. Efficiency is obviously 0 at 0 because you're not getting any useful power out of this. You're not going anywhere. 0 speed advance also corresponds to the largest angle of attack. So alpha equals alpha max equals theta, which is also why you get the most power or force or torque out of this. Again, efficiency is 0, no useful work being done by a stationary propeller. And that as advanced speed increases, thrust and torque decrease. So their torque going down, force going down. Power generally goes down as well. But efficiency is going to increase to some maximum value. We see in both cases I have some maximum value of efficiency and some value of the speed of advance coefficient. Same thing for the aerial applications, have some maximum value. And then after that maximum value goes down, back down to 0, as my thrust goes down to 0 as well. So those are the general curves for thrust, torque, and power coefficient for these propellers. As I said, generally the easiest thing to do is to find values of CF, CT, or CP based on speed of advance. So whatever the velocity coming in is, diameter and revolution speed, I can find some value for CF. Once I find that value for CF, I can come back here, plug that in for CF, and based on the other parameters going on, I can find FT. So if I want to find, as I said, CF at a value of 0.6, I know it's roughly 0.55 maybe from this graph, so that plug in for that. I know all these values down here, so solve that for my force of torque, and for my force of thrust. And at that point, I can find force of thrust much easier than trying to figure out how all this stuff depends on the angles and do those integrals. So generally, this is how it's done using these graphs. Another thing that's done a lot is something called variable pitch. So you can actually twist, you have actuators or something at the hub of the propeller blade, and they can rotate the propeller blade around and give you variable pitch. And that's going to increase performance. As you can see, have some certain efficiency curves for different values of theta. And you see as theta changes, I get different efficiencies. And so if I want to have something that speeds up, or something that can handle different speed of advances. So if I'm looking at a wind turbine and the wind is always a constant, say 10 miles an hour, and my speed of advance is always kind of the same number, I don't necessarily need variable pitch because I'm always going to be at some particular value. And so just play with my angle theta and get that to basically the optimum value that I want. But if I'm in a situation where this wind speed changes a lot, my rotational speed changes a lot, so my speed of advance changes a lot, I want to be able to change my angle theta and hit the maximum efficiency curve, because that's obviously going to give me better performance out of my wind turbine. So allowing for this variable pitch angle, you can achieve improved efficiency over a wider range or speed of advance, as you would with a fixed pitch blade. Obviously, though, downside of that, it's going to come at a cost, increased complexity, because you need all these actuators and things and control systems to actually twist your blades around. So in some cases it's worth it, in some cases it's not, as the case in most designs. So that is the basics of wind power and wind propellers. Next class we'll get into a bit more of the details.